Hello, my name is Uwe Ortmann from PicoQuant, Berlin, Germany. I'm standing here with Karl Gryczynski from the TCU Fort Worth. He's also professor at the Texas North University, also in Fort Worth. Karol, what has inspired you to go into the research field of time-resolved fluorescence?
It's kind of interesting thing because eventually I grown with fluorescence in Poland. That's where eventually I learned fluorescence, but it was basically steady state. The first contact I had with time resolve was essentially when we worked with University of Toruń, where eventually first frequency domain system was built. And eventually later on I went as a research assistant professor to University of Maryland, where I worked with Dr. Enrico Bucci, and we did time resolve measurements with the Center for Fluorescence Spectroscopy at this time using hemoglobin. So the possibility of having a time resolve information and at this point having all the information about the dynamic of the system and changes within a nanoseconds and sub-nanoseconds timescale was the most interesting things in the field. That's why we were everybody was pushing at that time to do the time resolve, and time resolve with highest resolution. At that time was 10 gigahertz frequency domain system, which was essentially giving us an access to picosecond timescale. So possibility of getting a time resolve information about dynamic processes, that was kind of attractive for everybody who went to time resolve.
So what was the most striking invention in this time? What would you say would help your research the most?
20 years ago?
In this 20 years time?
Let's say kind of funny, because when I was starting, the big thing was essentially a possibility of doing the amplifying at high frequency range, and frequency domain was dominant technology. And eventually two things happened which changed a lot. It was development of reverse time-correlated single photon counting, where we can do the measurements in time domain much faster, because originally we were going in hours sometimes. So we were able to turn this to minutes or long minutes, depending on the length of the lifetime. So this was a kind of big change, and it was kind of surprising for us coming from frequency domain when we were moving to time domain. And one thing which helped in this was essentially development a solid state laser source, pulse laser sources, which eventually changed the field completely. So we can have right now any laser source with any wavelengths, pulsed with picoseconds or femtosecond resolutions. And they were essentially two things which change everything. And now time-resolved technology becomes commonly available. We can do essentially everything for reasonable price, I would say now.
So how would then be an ideal instrument for time-resolved spectroscopy look like? What do you think should be the core components?
You know, it's hard to say, because it's number of things which happened. You know, we have a strict camera in the field, which is a really good system that requires huge amount of light. So it's not many biological applications yet, unless they change something in technology. Time-correlated single photon counting gives us this one very important thing, that the data are easy to interpret. So the system becomes kind of easily accessible by new guys. And that's what is important, because everybody understands what is going on. In frequency domain, it was much more difficult. After 10 years working, you look on these curves, you knew what they mean. In time domain, you can see this right away. So this is essentially a major change. And at this point, these applications will be quite important. And of course, imaging, which comes with microscopy, time-resolved imaging, which put us to the molecular information on a cellular level, essentially makes big changes. And I think now we have to look how to apply this to whole body imaging using time resolve. We have a lot of imaging in sense of intensity imagers. We have, of course, PET, we have MRI, we have all this stuff. We don't have anything in optical, which would be, we have diffuse tomography, which has a lot of troubles in the field. But now I think times comes also for us to try to apply this to the imaging field in sense of imaging of small animals or even human body in the future.
So would you see that the instrument would be smaller, more compact, and then finally in any doctor's office or in any hospital?
You know, it becomes quite easy to integrate these instruments, which are relatively big, to essentially almost a pocket type of instrument. So it will be probably everywhere. Essentially, even a simple way of coding information by different lifetimes and measuring this could be important for fraud protection with credit cards. And obviously, it would be something obvious to have a diagnostic device which can be used to monitor any kind of markers, physiological markers, starting with cardiac markers or cancer markers, where we can do essentially very, very precise monitoring. An advantage of time-resolved approach like this one, which gives us first of all, possibility of gating, and if we use proper dies, we can essentially achieve a huge improvement in sensitivity. And right now, what we are doing, we are coming with new technology where we can use these dies with multi-pulse pumping, and we can increase another order of magnitude sensitivity. So this becomes essentially a crucial application. And at this point, if we can separate the background from our signal, then we can do the detection on very low level. And for biomolecular markers, this is a key component. We have to detect something in a picomolar range with the huge background from the tissue, because human body is a factory, very dirty factory of everything. So we have to have something very specific just looking for this, what we want to detect.
So the future needs a very compact, very sensitive machine, easy to operate.
Easy to operate, yes. And you know, this is a still sophisticated measurements. We have to remember it's essentially a lot of hidden possibilities for an error. So we have to kind of simplify this to that point that eventually we will be free of any kind of artifacts. And eventually, if we're looking for the diagnostic, we don't need a precise information about how molecules move. We want to know if they are there or not. So it becomes easier. So that would be essentially a compact device. And like in many cases, medical professional, because it wouldn't be a doctor probably, it would be just a medical professional, doesn't have to know how it works. It just needs the results. Yes, we scientists are rather looking how it's happening, what we are looking for. But here would be a compact device. And from perspective of commercialization, like you guys, we are thinking about something which is simple, not expensive, but you can sell millions of them. Yes, that's how it works.
That's how it works. Thank you for your insight in the future of time-lapse spectroscopy. Carol, thank you.
Thank you very much.